All right, so let's pick up where we left off on the last tutorial. We were showing the problem-solving strategy and how to relate position, time, velocity, and acceleration. So now I want to do a fairly important derivation. I'm going to try to create a new equation from the existing ones. To do that, I'm going to do it on a separate sheet or on a smart sheet. I want you to maybe what I'm writing down is write it in this area, nice and organized. I'll try to organize it on my sheet. I just can't write it in such a small space, but I think you can do that. Okay, so let me go to a different sheet. Our goal is this. You don't have to write this down. I want to find a equation for x as a function of time. In other words, where are we as a function of time and acceleration, and knowing that we're accelerating. Let me remind you, if we're not accelerating, right? In other words, if a is 0, we already know how to do that. X is simply equal to average speed times time. Okay? Plus wherever we start. I want to be able to do that where I have acceleration in my equation. I'm going to refer back to the equations at the top of your first page. So when I do that, you should see it in front of you because you're still on the first page while I'm on a different page here. Okay, so where do I start? Well, the hardest thing for kids is when I say derive this, I don't know where to begin. Well, I basically say I'm looking for an equation for position. So I want to start with an equation for position. Right now we only have one. So step 1, our equation for position is equal to x equals x naught plus average velocity times time. Okay, so I don't want acceleration. I don't want average velocity in there. I want acceleration in there. So I'm going to do a substitution. In other words, I'm going to get rid of this by substituting in another equation for it. So I'm going to put to the side here where average velocity, so what's an alternative equation, average velocity? Well, I don't want to do change in position over time because it's just this equation all over again. I want another one. That's the v naught plus v all over 2. So I'm going to substitute that in. So in my next line, I'm going to say, and I'm going to move the x naught to the, no, I'll leave it. No, I'm going to move it over. So I'm going to change x minus x naught equals, what's average velocity? I'm going to put v naught plus v all over 2, put parentheses around it, all multiplied by time. Okay. So I've gotten rid of the average velocity part. I want to get acceleration in there. So I don't want to figure out the position based on final speed because usually I don't know how fast I'm going at the end. If I just say I'm initially going this, and this is my rate of acceleration. In fact, if I go back up here, maybe I should have made this clearer. The third thing we want to express it in terms of is the initial speed, right? Because that's usually has to be given. I can't know how far I'm going unless I know what I'm doing initially. So I'm going to keep the initial speed in there, but I want to get rid of the final speed. So I need to substitute that out. So I can go to equation 3 at the top of our sheet, and I can say where v is equal to v naught plus at. And that's where I get my a in there. So now I can write my third step, x minus x naught equals v naught plus, now I'm going to substitute in for v, what I just put. So I'm going to put, I don't need to put parentheses, v naught plus at all over 2 times t. Now I get to simplify. The rest is algebra. So I'm going to go over here, step 4. Ooh, this is way out of whack. I'm going to call x minus x naught delta x. That's simply just my change in position. Equals. Okay, what's v naught plus v naught? That's 2v naught. So I'm going to have 2v naught. At is plus at all over 2, all multiplied by t. Okay, now I'm going to do one last step. I'm going to do 2 steps in one. I'm going to distribute the t throughout, and then I'm going to split up these to the numerator. So, see if you can follow. I'm going to have 2v naught times t divided by 2. So 2 divided by 2 is 1. So that becomes delta x equals v naught t. Oh, there we go. Our change in position is simply how fast we're going initially times time. Then there's the plus. So if I distribute the t, I have an at squared in there, and I still have to divide by 2. So that simply just becomes 1/2 at squared. And there is our equation. This is probably the most useful equation of the 5 that we're going to have. So this is in your reference tables, but under equation 4, you can write my change in position equals how fast I'm going multiplied by time. Now let's stop there. If I'm not accelerating, then this is exactly what we'd expect. If I am accelerating, then I have to add a term on based on my acceleration, 1/2 AT squared. Oh, okay. Now I'm going to write off the margins. Look at this part. Isn't this saying that delta x is proportional? Let's say we're initially not moving, so that this term is 0. This term is 0, okay? Don't cross it out on your sheet. But if we're initially not moving, we're starting from rest, it's simply delta x equals 1/2 t squared. That's saying our change of position is proportional to t squared. We already know that from our graphs. X versus t when you're accelerating looks like that. There is your proof of that algebraically. Okay, now let's go back and apply this equation to part D and see if we get our answer of, I believe it was 12. So I would say delta x equals, I'm not going to rewrite the equation because I have it over here. What's V naught? 8. How much time? 6 seconds. Plus 1/2 A. Now this is going to be careful. Remember, A is the -2 times 6 seconds squared. Okay, so 8 times 6 is 48. Plus, let's see, 6 squared is 36. Half times -2 is -1, so that's -36. Add them, I get 12. Boom. There's my answer. That's sweet. Okay, so again, this is the most important equation of the lot. And because it has built into it our delta x equals v naught t, and then it has an additional term when you're accelerating. So in your reference tables, you will see that and not equation 1. Equation 1 is built into equation 4. All right, so there's one last equation that's helpful. I'm not going to derive it. In fact, I'll probably leave it for a quiz or a homework for you to derive it. It's the same process I just did. And it's an equation. So if I go up to equation 3 tells us how fast we're going as a function of time. Well, wouldn't it be nice to have an equation for how fast we're going as a function of distance? So let's say I'm in a car and I'm going a certain speed and I accelerate over a distance of 10 meters or 100 meters. How fast am I going at the end? Well, you could try to use that distance to find a time and then use equation 3, or it would be nice if we could just directly do it. So it would require derivation, like I said, similar to what I did there, but I'm just going to give you the final result. So the equation for speed as a function of displacement is as follows. V squared, so right away it's unusual and it's solved for the square of the final speed, equals your initial velocity squared plus a term to your acceleration. And that term to your acceleration is twice your acceleration times your change in position. So that's also in your reference tables. You don't have to memorize it, you just got to know when to use it properly. Okay, so let me finish up with an example or two. Whoops, I don't want that. So I'm going to go to the back. I'm going to try to do examples 2 and 3, and then we'll talk about 4 in class. So I'm going to have to hustle. All right, so how far does a cat travel if it accelerates from rest to speed of 6.7 meters per second in 2.1 seconds? Okay, so I'm going to go through the process. I'm going to first figure out what do I want. I want how far. How far is position, so I'm going to go over to the table and I'm going to put delta x. Okay, next, what information do I have? It accelerates at rest, from rest. That's v naught. Okay, to a speed of 6.7 meters per second. That's v. Time is t. Okay, so my v naught is going to be 0. My v is 6.7. My time is 2.1. I don't have acceleration information. So how would I calculate x? Ooh. I do have an equation that allows me to get it from this, this, and this. It just might not be obvious. Okay, so let's say you want to use that fourth equation. I want to find a. So I'm going to do this in 2 stages. I'm going to find a first. A is going to be delta v over t. Okay, so my delta v is 6.7 minus 0 all over 2.1 seconds. Okay, so when I divide those, I get 3.2 meters per second squared. Now I can apply my new equation where I'm looking for, so now I now know this is 3.2. So I can say, all right, x, my change in position, is equal to v naught t plus 1/2 at squared. Okay, this term is 0 because our initial speed is 0. So my change in position is 1/2 of 3.2. And don't forget to square your time. So this is 2.1 seconds squared. And if I punch it out on my calculator, I get 7 meters. Okay, 7.0 meters. So let me point out a few mistakes that students often make when they see this. They'll just say x equals vt, and they'll put in 6.7 multiplied by 2.1, and they'll get an answer of about 14, which is not coincidentally twice the value of this. So don't do this. First of all, there is no equation that says x equals vt. It's x equals average speed times time. Some of you might have recognized a simple way of doing this without using acceleration, and you could have. I'm not going to go through it all, but I could have said x is v bar t, right, where v bar is initial plus final divided by 2 times time, and then gone and do that directly. So that will work as well. B, if the acceleration was same but for 1.5 times the time, by what factor would the distance increase? So I want proportions. So I need an equation that relates position and time, and that's basically x equals 1/2 at squared. I can ignore the v naught t because v naught is initially 0. So that says x is proportional to t squared. So I can say x2 over x1 equals t2 over t1 quantity squared. So t2 over t1 we're told is 1.5, so that's 1.5 squared, which is 2.25. So we're going to go a little bit more than twice the distance when we only go 1.5 times the time. All right, lastly, at the scene of an accident involving texting teens. So this is a whole different problem. All right, an investigating officer measures the length of tire skids to be 60 meters long. It is also known that the car's braking acceleration is negative 3.8. How fast were the distracted teens moving when the brakes were slammed? All right, this is actual what forensic police officers can do. They can look at the length of the skid marks from a tire. They measure that length. Knowing something about the car, they can know what the acceleration should have been, and they can figure out how fast you're going and if you were speeding. So what are we looking for? How fast? So that's a speed. Were the teens going when the brakes were slammed? Okay. So this is a little bit, you got to interpret that. Is that the beginning of the event or the end of the event? And if it's, we're just, nothing's happening until we slam on the brakes, that's the beginning. So we're looking for initial speed. All right, we need 3 pieces of information. So I go through here, they measure the length of the tire skids to be 60, so x or delta x is 60. Okay, it's known the car's braking acceleration, that's explicit, 3.8. And how fast when the brakes were slammed? Oh, we don't seem to have a third piece of information. We have 0 information about time. Do we know anything about the final speed? Yeah, generally when you slam on the brakes and your skid marks are 60 meters long, that assumes you come to a stop. So our final speed is 0. Okay, so what equation ties together? We don't have any information about time. The tendency for students is to try to solve for time. Don't. Just directly use the equation we have where we can say v squared equals v naught squared plus 2a delta x. I want to solve for initial speed, so I'm going to bring it to the other side. So I'm going to say negative v naught squared equals, no, I don't know why I'm doing that. That's silly. I'm just going to leave it on the right-hand side, move everything to the left, so I can say v squared minus 2a delta x equals my initial velocity squared. Okay, I'm going to plug in numbers here. So my initial speed, or final speed is 0, so my answer is negative 2 times negative 3.8 times 60. Okay, now remember that's v squared. So I'll do that. So 60 times 2 is 120. 120 times 3.8 is 456. So I can say v naught squared is 456. Therefore, my initial speed is the square root of that. And if I take the square root of that, I get 21.3 meters per second. All right, so that's about almost 50 miles per hour. There's your introduction onto 2 new equations and how to apply them. We will do more practice with a homework set. If you want to take a challenge, you can do number 4, but you don't have to.